They built entire railroads, 50 miles of track, bridges across canyons, trestles over rivers, switchbacks carved into mountainsides, complete railroad systems with locomotives, rolling stock, repair shops, and crew quarters. And when the last tree fell, they ripped up every rail and moved on to the next forest. This wasn't some small operation with a few handcars. These were real railroads, the kind with whistles that echoed through mountain valleys at dawn, the kind with dispatcher offices and telephones and timetables, infrastructure that would have cost millions in today's money, built to harvest one stand of timber, then abandoned or dismantled within 5 to 10 years. Between 1880 and 1960, American logging companies constructed over 30,000 miles of these temporary railroads. That's more track than some European countries ever built for their entire national rail networks. More track than exists in countries like Switzerland or Belgium today. And almost none of it remains. The men who built these lines worked in conditions that would shut down any modern construction site. They blasted grades through solid granite in winter. They laid track across trestles so rickety that locomotives would sometimes punch straight through. They rode loaded trains down mountain grades so steep that a failed brake meant certain death. And when the timber companies were done, when every marketable tree had been felled and shipped to the mills, they pulled up the spikes, loaded the rails onto flat cars, and left nothing behind but stumps and rotting cross ties. This is the story of America's forgotten railroads. The lines that built this country's cities then vanished, like they were never there at all. To understand why anyone would build a railroad just to cut some trees, you need to understand what American forests looked like before the logging era. The Pacific Northwest alone contained an estimated 1.1 trillion board feet of timber at the turn of the 20th century. That number is almost impossible to comprehend, so let's break it down. A single Douglas fir could yield 30,000 board feet of lumber. That's enough wood to frame 5 average houses from one tree. And there were millions of these trees, stretching from the Pacific Ocean to the Cascade Range, from Northern California to British Columbia. These trees were enormous in a way that modern Americans rarely see. The coastal redwoods reached over 350 feet tall. Old-growth Douglas firs ran 200 to 250 feet, with trunk diameters of 8, 10, sometimes 12 feet. Western red cedars lived for 1,000 years and grew so large that early loggers would spend an entire day just felling one tree. Not because they were slow, because the tree was that big. Imagine standing at the base of one of these giants. You can't see the top. The trunk is wider than your outstretched arms can reach, wider than a car, wider than some buildings. The bark is a foot thick, furrowed and ridged like the skin of some ancient creature, and it goes up and up and up until it disappears into the canopy above. Now multiply that tree by millions. Virgin forest, stretching in every direction. Trees so dense that sunlight barely reached the forest floor. The air thick with the smell of cedar and rotting wood and moss. Silence so complete that you could hear a branch fall from half a mile away. This was the Pacific Northwest, before the loggers came. The same story played out across America. The white pines of Michigan and Wisconsin, the longleaf pines of the Gulf Coast, the spruce forests of Maine. Everywhere you looked, there was timber worth more than gold. And at turn-of-the-century prices, that comparison wasn't an exaggeration. A single trainload of old-growth logs could be worth more than a working man earned in a decade. A single forest could make a family rich for generations. The problem was getting the timber out. These forests grew in some of the most rugged terrain on the continent. Steep mountain slopes, deep river canyons, soil so saturated with rain that it would swallow a wagon to its axles. The trees grew where roads couldn't go, where wheels couldn't turn, where men could barely walk. In the early days, Loggers used rivers to move timber. They'd fell trees near streams, roll the logs into the water, and float them downstream to mills. Log drives became legendary events in places like Maine and Wisconsin. Crews of river pigs would ride the floating timber, breaking up jams, guiding the logs around obstacles, sometimes dying when a jam broke loose and buried them under thousands of tons of moving wood. But rivers only ran certain directions. They dried up in summer and froze in winter. They wrapped around mountains instead of going over them. And the best timber often grew miles from any navigable water. Oxen teams could drag logs, but the numbers were pitiful. A team of 12 oxen, working hard all day, might move one log at a time over rough ground. That's not efficiency. That's desperation. You'd spend more on feeding the animals than you'd earn from the timber. Steam donkeys helped. These portable steam engines could winch logs across the forest floor using cable systems. A skilled donkey crew could yard logs from a quarter-mile away, pulling them through the underbrush with massive steel cables. It was a massive improvement over oxen. But the donkey engine had limited range. You still needed to get those logs from the landing to the mill, and the mill might be 30, 40, 50 miles away, over mountain passes that no wagon could climb. The economics made the decision inevitable. A logging railroad could move more timber in a single day than an oxen team could move in a month. One locomotive pulling 20 cars, each loaded with 3 or 4 massive logs, running multiple trips per day. The math was overwhelming. The math was undeniable. Consider a typical operation in the Pacific Northwest around 1910. A company might acquire timber rights to 50,000 acres of old-growth forest. That land contained somewhere between 500 million and 1 billion board feet of marketable timber. At contemporary prices, that timber was worth between $5 and $15 million. Building a railroad to access that timber might cost $300,000 to $500,000. Expensive, certainly, the equivalent of tens of millions today. But compared to the value of the timber, it was a bargain. The railroad would pay for itself in the first year or two of operation. Everything after that was profit. The Weyerhaeuser Timber Company understood this math better than anyone. By 1910, they owned over 2 million acres of Pacific Northwest timberland. They operated multiple logging railroads simultaneously, some running over 100 miles of track. Their railroads weren't sidelines. They were central to the business model. And here's the part that seems almost insane from a modern perspective. When the timber was gone, that $500,000 railroad became worthless. You couldn't run freight over it because the only freight had been logs, and there were no more logs. You couldn't run passengers because nobody lived there anymore. The towns that sprang up around logging camps would disappear within months of the last tree falling. The stores would close. The boarding houses would empty. The camps would rot. So they salvaged what they could. The locomotives went to other operations. The rails were pulled up and shipped to the next forest. Sometimes the bridges and trestles were dismantled. More often, they were simply abandoned to rot. The timber companies didn't see this as waste. They saw it as cost recovery. Better to pull up those rails and reuse them than leave them rusting in the mountains. The railroad was never the point. The railroad was just a tool, like a saw or an axe. You don't mourn throwing away a worn-out axe handle. Building a logging railroad bore almost no resemblance to building a mainline railroad. When the transcontinental railroads went west, they surveyed routes for months. Engineers calculated grades to the decimal point. They built to last a century, designing structures that would carry trains heavier than the ones that existed at the time of construction. A mainline railroad couldn't exceed a 2% grade, because conventional locomotives couldn't climb anything steeper while pulling heavy loads. Every curve was measured. Every bridge was tested. Every spike was driven according to specification. Logging railroads threw all of that away. A logging railroad needed to be built fast and cheap. The timber companies were racing against fire, against competing claims, against the seasonal windows when logging was even possible. Every month the railroad wasn't running was money left in the forest. money that could burn in a summer wildfire, money that could rot in the winter rains, money that competitors might take if you moved too slowly. Survey crews would walk the route once, maybe twice. They'd mark a general path, identify the worst obstacles, and move on. Detailed engineering could happen later, or not at all. If a route didn't work, they'd abandon it and try another. The cost of a failed survey was nothing compared to the cost of delay. Construction crews followed within days, sometimes within hours. These weren't the massive labor gangs that built the transcontinentals. Those projects employed thousands of men, whole armies of workers stretched across hundreds of miles. A logging railroad might be built by 50 men, sometimes fewer. They used whatever materials were at hand, which in a forest usually meant the forest itself. Crossties came from trees felled along the right-of-way. If a suitable tree stood where the track needed to go, you cut it down and turned it into ties on the spot. Why haul in ties from somewhere else when you're surrounded by wood? The ties weren't treated with creosote or any other preservative. They were green wood, freshly cut, spiked to the rails while they still oozed sap. They'd rot within a few years, but the railroad wouldn't be there in a few years anyway. Ballast was whatever rock you could dig from the grade. Sometimes there was no ballast at all. Rails sat on raw earth, on ties laid directly on the mountainside. The track would settle and shift with every passing train. Maintenance crews would follow behind, respiking rails, adjusting grades, making corrections that would last until the next heavy load came through. The grades these crews built would have horrified any mainline engineer. 5% grades were common. 7% wasn't unusual. Some logging railroads included sections of 10% grade or steeper. That's a rise of over 500 feet per mile. Conventional locomotives couldn't have climbed them at all. They would have stalled, wheels spinning uselessly, steam pressure bleeding away into nothing. And the curves. Mainline railroads built sweeping curves with radii measured in thousands of feet. A sharp curve on a main line might be 4 or 5 degrees. Logging railroads built curves so tight that locomotives would nearly touch their own cars as they went around. 15-degree curves, 20-degree curves, curves where the rails seemed to fold back on themselves. Switchbacks were common. The train would climb 50 feet, stop, reverse direction, climb another 50 feet, stop, reverse again. Back and forth up the mountainside, like a snake ascending a staircase. The Simpson Logging Company Railroad in Washington State included one section with 23 switchbacks in 5 miles. The train would crawl up the mountain in a zigzag pattern, the crew stopping at each switchback to throw the switch and reverse direction. A trip that covered perhaps a mile in straight-line distance required traveling nearly 10 miles of track. It might take an hour to cover that single mile of elevation gain. These weren't engineering compromises. They were acts of desperation performed at speed. Trestles presented the most dramatic example of logging railroad construction philosophy. When a mainline railroad needed to cross a canyon, engineers would design a steel or stone structure intended to last indefinitely. The process might take years. Surveys and calculations and material procurement and construction and inspection. A major railroad bridge was a statement of permanence, a declaration that this railroad would exist forever. When a logging railroad needed to cross a canyon, the crew built a wooden trestle in days, sometimes hours. These trestles used green timber cut from nearby trees. The logs weren't milled, they weren't treated. They were round logs, bark still attached, notched at the joints, and spiked together with massive iron spikes. A 200-foot trestle might be built entirely from timber, harvested within a few hundred yards of the crossing. The structures were terrifying to look at. Spindly towers of raw logs, seemingly held together by faith and a few iron spikes, supporting tracks that swayed when locomotives crossed. You could stand beneath one of these trestles and look up through the gaps between the deck planks. You could see daylight. You could see the rails above you. You could wonder how any of it held together. Crewmen described the sensation of crossing certain trestles as feeling the entire structure bounce beneath the weight of the train. You could hear the wood creaking. You could feel the deck tilting slightly as the locomotive's weight shifted from one bent to the next. Some engineers refused to look down during crossings. Others developed rituals, touching specific parts of the locomotive cab for luck before starting across. And yet the trestles held. Not because they were well engineered, but because they were massively overbuilt. When you're using whole logs instead of milled beams, you end up with more strength than you technically need. A 12-inch log has far more structural capacity than a 12-inch milled timber of the same wood. The margin of error made up for the lack of precision. When trestles did fail, they failed catastrophically. A locomotive breaking through a rotten trestle would drop straight down, carrying cars and crew with it. There was no slow collapse, no warning. The deck would simply give way, and everything on top of it would fall. The Weyerhaeuser Company lost an entire train on a trestle collapse near Longview, Washington, in 1924. The locomotive, 17 loaded cars, and 5 men went off a curve at estimated speeds over 40 miles per hour. The locomotive punched through the trestle deck like it was made of paper. One moment, there was a train. The next moment, there was falling wood and screaming steel and men shouting, and then nothing but the sound of fire. The wreckage was still burning when rescuers arrived hours later. They found 3 bodies. 2 men were never recovered, presumed buried under logs and debris that no one had the equipment to move. The men who built these railroads worked in conditions that would be considered criminal negligence today. They started at dawn and worked until they couldn't see. There were no 8-hour days in railroad construction. There was light and there was dark, and you worked during the light. In summer, that meant 14 or 15 hours. In winter, when the days were short and the weather was brutal, you worked until the foreman said stop, and the foreman never said stop until the darkness forced the issue. The pay was decent by the standards of the era. A railroad construction hand might earn $2 to $3 per day, plus room and board at the company camp. Skilled workers earned more. Powdermen, who handled the dynamite, track foremen, who coordinated the crews, bridge builders, who supervised the trestle construction. But everyone earned their money. Summer construction meant heat, mosquitoes, and the constant threat of forest fires. The smoke from slash burning hung over construction camps for weeks at a time. Men developed chronic respiratory problems that stayed with them for life. They coughed up soot and breathed through wet bandanas, and kept working because stopping meant losing your job. Winter construction was worse. In the mountains of the Pacific Northwest, snow could fall from October through May. Crews lived in canvas tents or rough-built bunkhouses, cutting grade through frozen soil, sometimes tunneling through snowdrifts just to reach the work site. Frostbite was common. Men lost fingers, toes, ears. They wrapped themselves in whatever cloth they had and kept swinging pickaxes into ground frozen hard as concrete. Injuries were constant, and treatment was minimal. A company might have a camp doctor, or it might have a first aid kit and instructions to get the injured man to town when you could spare someone to take him. Broken bones, crushed fingers, powder burns, all of it happened daily, and most of it was treated on site. You splinted what you could. You bandaged what you couldn't. You hoped the infection stayed out and the bone set straight. The dead were buried where it was convenient. Small cemeteries dotted the logged-over forests of the Pacific Northwest. Wooden markers rotting away within a generation. The names of the men who built these railroads vanishing along with the railroads themselves. No one counted these deaths with any precision. No one recorded the names in any central register. A man would die, his fellows would bury him, and the work would continue. The locomotives that ran on logging railroads were unlike anything on mainline tracks. Conventional locomotives used a direct connection between the pistons and the driving wheels. The steam pushed a piston, the piston turned a crank, the crank rotated the wheels. Simple, efficient, and completely useless on logging railroad grades. The problem was torque. A conventional locomotive could pull enormous loads on level track, but it couldn't climb a 10% grade with a loaded train. The wheels would simply spin. The connection between power and wheel rotation was too direct, like trying to drive a car up a steep hill in high gear. You'd have plenty of engine power and no ability to use it. The solution came from a Michigan inventor named Ephraim Shea in 1880. Shea was a logger himself, and he understood the problem from personal experience. He'd watched conventional locomotives fail on grades that his business required him to climb. His design used a completely different power transmission system. Instead of driving the wheels directly, Shea's design used the steam pistons to turn a horizontal drive shaft running along the right side of the locomotive. This drive shaft connected to the wheel axles through a series of bevel gears. The gearing reduced the speed of wheel rotation while multiplying the torque. Think of it like a bicycle's low gear. You pedal faster, but you can climb hills that would be impossible in high gear. The Shea locomotive traded speed for pulling power. The result was a machine that could climb grades that would have stalled any conventional engine. Shea's could manage 7, 8, even 10% grades while pulling loaded log cars. They were slow, rarely exceeding 12 miles per hour even on level track, but speed wasn't the point. Getting up the mountain was the point. The Shea design looked strange, almost alien. The offset drive shaft made the locomotive visibly asymmetrical. The boiler sat left of center to balance the weight of the machinery on the right. The cylinders were mounted vertically on the right side, looking almost like they'd been stuck on as an afterthought. The whole thing appeared lopsided, somehow wrong, like a machine that shouldn't work, but somehow did. Lima Locomotive Works in Ohio built nearly 2,800 Shea locomotives between 1880 and 1945. They became the definitive logging locomotive, so successful that the name Shea became almost synonymous with geared steam power. When loggers talked about their locomotives, they often just called them Sheas, regardless of what they actually were. Running a Shea was a different experience from running any conventional locomotive. The vertical cylinders created a distinctive chugging sound, a rapid exhaust beat that echoed through the mountains. Old-timers who worked the logging railroads can still describe that sound 60 years later. It was the heartbeat of the industry. The geared drive made the entire locomotive vibrate in ways that mainline engineers found unsettling. Everything felt slower, more deliberate, more mechanical. You could feel every gear tooth engaging. You could feel the power transferring from the drive shaft to the wheels. The locomotive seemed alive in a way that conventional engines didn't. The Climax locomotive, developed in Pennsylvania in the 1880s, used a different approach. Instead of an offset drive shaft, the Climax placed its cylinders at angles, driving a central crankshaft that connected to the wheels through bevel gears. The design was more symmetrical than the Shea and handled rough track somewhat better. Where a Shea would roll and pitch on uneven rails, a Climax would track more steadily. The Heisler locomotive, introduced in 1892, split the difference. It used two cylinders mounted in a V formation, driving a central drive shaft that connected to the wheels through gearing. The Heisler was faster than the Shea on decent track, though less powerful on the steepest grades. Each design found its advocates. Logging companies chose their locomotives based on the terrain they faced, the track conditions they could maintain, and sometimes simple preference. Some operations ran all three types. Others swore by one and refused to consider alternatives. What they all shared was the ability to do what no conventional locomotive could do. They could crawl up mountainsides on rails that would have derailed any mainline engine. They could negotiate curves so tight that they seemed impossible. They could keep running on track so rough that the entire locomotive would pitch and roll like a ship in a storm. The engineers who ran these machines developed skills that no mainline railroader needed. They learned to read the track ahead by feel, sensing when a rail was about to give way before they could see any problem. They learned to manage trains on grades so steep that a moment's inattention could mean a runaway. They learned to trust equipment that seemed barely capable of surviving each trip. Running a loaded logging train down a mountain grade was perhaps the most dangerous regular job in American industry. The physics worked against you every moment. A loaded log train might weigh 400 tons or more. On a 5% grade, gravity exerted over 20 tons of force pushing that train downhill. The only thing keeping it from accelerating into oblivion was the brakes. Early logging trains used hand brakes exclusively. Every car had a brake wheel mounted on a small platform at one end, and brakemen rode the cars, tightening and loosening the brakes as conditions demanded. On a loaded descent, a brakeman might spend the entire trip leaning on his brake wheel, muscles burning, sweat freezing on his face in winter, knowing that if he let up for even a moment, the train would begin to accelerate. Picture yourself on one of these descents. You're standing on a tiny platform at the end of a log car, exposed to the weather, hands wrapped around a cold iron wheel. The track curves away below you, disappearing around the mountainside. You can hear the brake shoes screaming against the wheel flanges. You can smell hot metal, the friction turning brake shoes to dust. The train is moving faster than you want it to, faster than feels safe, and your arms are already exhausted from holding the wheel. One slip, one moment of weakness, one brake shoe that wears through at the wrong instant. That's all it takes. Air brakes eventually replaced hand brakes on most logging railroads, but the technology couldn't always be trusted. Airlines leaked, brake shoes wore down faster than maintenance crews could replace them. The moisture in mountain air could freeze brake lines in winter, leaving a train with no braking ability at all, just when you needed it most. Runaways happened regularly. A train would lose braking on a grade, begin to accelerate, and within seconds, reach speeds that no logging track could handle. What happened next depended entirely on the track ahead and the decisions made in the next few moments. Sometimes the track included escape switches, sidings that curved uphill, designed to slow a runaway by forcing it to climb. If the engineer could see the switch coming and had time to think, he might throw it and divert his train onto the escape track. The train would slow, stop, and everyone would walk away shaking and sick with adrenaline, but alive. More often, there was no escape track. The runaway would continue to accelerate until it reached a curve it couldn't negotiate, a trestle that couldn't support the speed, or a grade that leveled off enough to scrub some momentum. The crashes were spectacular and terrible. Log cars would leave the rails and scatter their loads across the mountainside. Logs weighing 10,000 pounds each would tumble free, bouncing down slopes, smashing through trees, crushing anything in their path. Locomotives would tip over, roll down embankments, sometimes explode when their boilers ruptured from the impact. The sound could be heard for miles. Crews had only seconds to jump before impact, and jumping from a moving train on a mountain grade was itself likely to be fatal. You could land on rocks, you could land on logs, you could roll down the mountainside until you hit something that stopped you permanently. Some men survived the jump, only to be crushed by the cargo that followed them down. The Blodell Donovan Lumber Company lost an entire crew in a runaway near Bellingham, Washington in 1918. The locomotive, 17 loaded cars, and 5 men went off a curve at estimated speeds over 40 miles per hour. The wreckage was still burning when rescuers arrived the next morning. They found 3 bodies. 2 men were never found at all. Their families never had graves to visit. Even normal operations could turn deadly in an instant. Couplers failed, separating trains on grades and sending unmanned cars hurtling downhill. Rails spread under load, dropping wheels into the gap and derailing trains at whatever speed they happened to be traveling. Logs shifted on curves, unbalancing cars and throwing them off the track. The men who ran logging trains understood these risks and ran the trains anyway. What choice did they have? The timber had to move, the mills had to be fed, the checks had to be cashed. Risk was simply part of the calculation, part of the cost that got figured into every board foot of lumber that left the forest. Some crews developed superstitions to cope with the danger. Engineers who wouldn't start a run without touching a certain spot on the locomotive. Brakemen who carried lucky tokens in their pockets. Firemen who said the same prayer at the start of every descent. These rituals made no physical difference, but they gave men something to hold on to when the physics turned against them. The veterans could tell stories that would make your blood freeze. Trains that caught fire on mountain grades. The crews trapped between advancing flames and certain death if they jumped. Locomotives that broke through ice while crossing frozen lakes, disappearing into black water with all hands aboard. Log cars that uncoupled on curves, the separated cars racing each other down the mountain, crashing together at the bottom in explosions of splintered wood. Every logging railroad had its ghost stories. The train that ran at midnight, years after the line was abandoned. The brakeman who still walked the grades, checking wheels that no longer turned. The whistle that echoed through valleys where no track remained. These stories weren't just entertainment. They were a way of remembering the dead, of acknowledging the price that had been paid. Logging railroads began to die in the 1920s, though the death was slow. The immediate killer was the truck. Logging trucks could go where rails couldn't, and they required no infrastructure investment. You didn't need to build a railroad to reach a timber stand with trucks. You needed a road, and roads were cheaper to build and easier to abandon. More importantly, trucks offered flexibility that rails never could. A railroad was committed. Once you laid the track, your route was fixed. If the best timber turned out to be half a mile from your line, you either extended the railroad or found some way to drag the logs to the existing track. A truck could just drive to the trees. The technology improved steadily through the 1920s and 1930s. Early logging trucks could carry perhaps 5,000 board feet of timber. By the 1940s, the number was over 20,000 board feet. By the 1950s, trailer configurations allowed loads that approached what a railroad car could carry. World War II accelerated the transition. The war demanded timber in enormous quantities. Spruce for aircraft, Douglas fir for construction, wood for everything from crates to barracks to shipbuilding. And the war demanded it immediately, not when a railroad could be built. Building a railroad took months. Building a road took weeks. The timber companies built roads. They also built trucks. The war produced massive advances in truck technology, advances that transferred directly to logging operations. Six-wheel drive trucks, diesel engines, air brakes, power steering, all of it came out of the war and went into the woods. By 1950, new logging railroad construction had essentially stopped. The existing lines continued to operate, some profitably, some through inertia. But no one was building new ones. The last major logging railroads survived into the 1960s. A few isolated operations continued even later. The Roaring Camp and Big Trees narrow gauge railroad in California, originally a logging line, still runs today as a tourist attraction. But as working transportation, logging railroads were done. What remains of them is surprisingly little. The equipment, the valuable equipment, was salvaged. Locomotives were sold to other railroads, to industrial operations, to anyone who could use them. Some ended up in museums, where you can see them today. The Georgetown Loop Railroad in Colorado runs a restored Shea locomotive. The Mount Rainier Scenic Railroad in Washington operates vintage logging equipment on track that once carried timber. Many were simply scrapped when no buyer could be found, cut up with torches, and sold by the pound for their iron. The rails were pulled up. Rail was expensive, and abandoned rail was free material for whoever claimed it. Salvage crews walked the old grades, pulling spikes, stacking rails, loading the iron onto trucks that drove where trains once ran. The wooden infrastructure rotted. Those trestles, built from green timber, never treated, never maintained once operations ended, collapsed within years. First the deck would sag, then the supports would crack, then the whole structure would fold in on itself, leaving a pile of moss-covered logs across the canyon floor. The cross ties followed. The grades themselves eroded, washed out by rains that no longer had tree roots to slow them. Today, you can walk old logging railroad grades throughout the Pacific Northwest. They appear as linear features in the forest, unnaturally flat pathways through the trees. The forest has grown back, second growth and third growth covering the stumps of the original timber. But the grades remain, engineered into the landscape, slowly being reclaimed but not yet gone. Occasionally you'll find hardware, a spike here, a piece of rail there, the rusted remnants of some piece of equipment too heavy or too worthless to salvage. Small artifacts of an industrial effort that once employed thousands and moved millions of tons of freight. The cemeteries are harder to find. Wooden markers vanished decades ago. Stone markers, where they existed, have been swallowed by vegetation. The names of the men who built and ran these railroads have largely been forgotten. They exist now only in company records stored in archives, in occasional photographs showing crews too tired to smile, in the memories of descendants who heard stories but can no longer say where their grandfathers are buried. But you can still trace what they accomplished. Those 30,000 miles of temporary railroad, built by hand, operated by skill and luck, dismantled when the trees were gone. They moved the timber that built San Francisco and Los Angeles, Seattle, and Portland. They fed mills that produced lumber for millions of houses, thousands of factories, hundreds of ships. The cities that spread across the American West in the early 20th century were built from trees that traveled over logging railroads. Every Victorian house in San Francisco, every bungalow in Portland, every craftsman in Seattle, the wood came from somewhere, and much of it came from forests that could only be reached by rail. The very idea of disposable infrastructure, build it fast, use it hard, throw it away, that idea helped create the modern economy. We don't think twice about replacing things anymore. We build knowing that what we build won't last forever. The logging railroads pioneered that approach when it was still considered wasteful, even sinful. We don't build like that anymore. We couldn't build like that anymore. The environmental cost alone would be unacceptable, setting aside the human cost that was simply accepted at the time. We've learned things about forests and watersheds and climate that the logging companies of 1910 didn't know and wouldn't have cared about if they had known. But something has been lost along with the recklessness. Those men, the ones who laid track across mountainsides, who ran locomotives down grades that should have been impossible, who died in numbers that no modern industry would tolerate. They had a relationship with the physical world that modern people rarely experience. They understood what steel could do, what wood could bear, what gravity would claim. They understood it in their hands, and their backs, and their bones. They understood it because their lives depended on understanding it. Every day, every trip, every mile of temporary track. When a brakeman felt a train starting to run away, he didn't check a digital readout. He felt it in the wheel under his hands, in the vibration through his feet, in the changing pitch of the rails. When an engineer sensed a trestle was about to give, he knew it from the way the locomotive moved, from sounds that no training manual could describe. This knowledge was earned through experience and paid for in blood. The logging railroads were wasteful and dangerous and often cruel. They stripped forests that had stood for centuries. They killed workers with an indifference that seems almost sociopathic from our modern perspective. They left scars on the landscape that are still visible 100 years later. And they built the world we live in. They delivered the raw materials of American expansion. They proved that impossible terrain could be conquered, that any obstacle could be overcome if the profit justified the attempt. The last logging railroad train ran sometime in the late 1960s. Nobody recorded the exact date. Nobody thought it was important enough to document. One day the trains were running, the next day they weren't. The locomotives went to museums or scrap yards. The rails went to whatever railroad needed them next. The men went to other jobs, or to retirement, or to the grave. 50 years of railroad building, 30,000 miles of track, hundreds of millions of tons of timber, hundreds, perhaps thousands of men killed. And when it was over, it ended quietly, without ceremony, like it had never happened at all. If you drive through the mountains of the Pacific Northwest today, through the Oregon Cascades or the Washington Olympics or the California Redwood Country, you're passing through landscapes that logging railroads transformed. The forests you see are regrowth. The old growth is gone, cut and shipped and turned into the structures that surround your daily life. Those trees traveled by rail, on lines that no longer exist, pulled by locomotives that were sold for scrap, operated by men whose names appear on no monuments and whose graves have been forgotten. The temporary railroads are gone, but what they built and what they cost remains with us still.